July 1917. As the Great War raged on, British and Canadian troops were at a stalemate with German forces near Ypres, Belgium. It had been a long and tiring deployment, with each second being an agonizing moment for every soldier. Some were hoping to get back home. Some wanted to see an end to the war. All of them wished to survive the global catastrophe. However, some of their hopes would not be fulfilled. July 12th, 1917 seemed like just another ordinary day in the trenches for the British and Canadian soldiers. They would hear the orchestra of German artillery rain down around them. It was a tune that they were accustomed to, yet this one had a slight change in it. After the initial bombardment, a yellow cloud would linger and creep towards the Allied lines. Despite quick orders down the trench line to equip gas masks, many would find themselves feeling their skin burning, vision slowly being impaired, and terrible blisters all over their body. They were exposed to a deadly new weapon: mustard gas. Mustard gas, or as it is called scientifically, sulfur mustard, is a chemical compound that is infamous for its usage as a chemical weapon and, ironically, as the first chemotherapy agent. It has both taken lives and saved lives. Sulfur mustard has been required to have been made around the mid-1800s. However, the chemical weapon that society knows it as could be credited to the father of chemical warfare himself, Fritz Haber. Haber was a German scientist and one of the top military researchers for Germany during World War I. He was an advocate for chemical warfare, continually pressing for the deployment at the start of the war. His work with a team of researchers led to the development of mustard gas. During the war, mustard gas was deployed in a number of ways. It could be dropped from bombers, placed in field artillery shells, and even unleashed from a grenade. The Allies, such as America, France, and Britain, would research their own mustard gas compounds. They would start to use their own mustard gas compounds in 1918 as the war ended. After the war, chemical weapons were banned under the Geneva Protocol of 1925. Despite this, sulfur mustard continued to see deployment during the interwar period, World War II, and even in the modern day. The most recent report of its use was by ISIS against the Syrian army in 2016. In this video, we will look at the basic properties of sulfur mustard and some of its functions. In other words, what can this molecule actually do? Then, we will look at the structure of this molecule using three different models. Finally, we will talk about the structure-function relationship of this molecule to learn how the structure of it creates a deadly chemical weapon we know as mustard gas. Note that we will focus on sulfur mustard as a weapon rather than as a cancer treatment. Now let's talk about the basic properties and functions of sulfur mustard. It has a chemical formula of C4H8Cl2S. In other words, it has 4 carbon atoms, 8 hydrogen atoms, 2 chlorine atoms, and 1 sulfur atom. It is a liquid at room temperature. When either a liquid or a gas, sulfur mustard has a pale yellow color in nature. It is infamously known for having a smell similar to garlic or, you guessed it, mustard. While it is soluble in many organic solvents, it has difficulty doing so in water. This information will become very important later on, so just keep a note of that. It is an alkylating agent, meaning that it binds to nucleophilic molecules like DNA and RNA. Nucleophilic molecules donate electrons in order to bond with other molecules. We will talk about them more later on. As a chemical weapon, sulfur mustard has a high penetrating power, as it is reported to pass through wood, cloth, leather, and even gas mask filters. Soldiers in the front lines were affected by the gas despite being fully clothed and covering their skin. Upon exposure, sulfur mustard can cause chemical burns, blindness, internal body pain, breathing problems, and potentially death. Because of its ability to cause numerous blisters, it is classified as a vesicant chemical weapon. A vesicant is a chemical agent capable of causing blisters. Now that the molecule's functions are out of the way, let's discuss the structure of sulfur mustard. We'll be looking at 3 different representations of it: a Lewis dot diagram, a skeletal structure, and a 3D model. Each shows a different aspect of our molecule that is fundamental to understanding the structure-function relationship. Let's begin with the Lewis dot structure. This is the only model out of the 3 to show electron behavior, which is very important to understanding the bonds between atoms. We can get a crude understanding of our molecule structure as well. It is a symmetrical molecule. The center has 1 sulfur atom. Connected to that sulfur atom are 2 hydrocarbons on each side. A hydrocarbon is simply a carbon with hydrogen attached to it. There are 2 hydrogens attached to each carbon atom. Now, That hydrocarbon is attached to another hydrocarbon, which, in turn, is connected to a chlorine atom. The dots around each letter represent the number of valence electrons in it. To maintain simplicity, valence electrons are the electrons located in the outer shell of an atom. For most atoms, a full shell of 8 electrons results in a stable atom, except for hydrogen and helium, which are full at 2 electrons. When atoms do not have a full shell, they open themselves up to sharing electrons with other atoms in order to satisfy their outer shell requirement. Bonds that form when atoms share electrons are called covalent bonds. So we can see that in our Lewis dot diagram, each atom has a full valence shell, meaning that there are no open spaces for outside atoms to bond with it. Now let's look at the shaded regions. This shading is done to represent electron density. Electron density is a probability of an electron being in a specific location. According to this diagram, there is a higher chance for electrons to be near the chlorine atoms as well as the sulfur atom in the middle. We will talk about this more in the structure-function relationship section further on. Since electrons are the key to creating bonds between atoms, the Lewis dot structure allows us to predict how bonds will form with our molecule. We will later see that sulfur mustard, as a chemical weapon, functions by bonding to some very important molecules in the human body. The skeletal structure, as the name suggests, is a very bare-bones look at our molecule. It shows only the most important atoms within it, atoms that dictate the function of our molecule. The black lines you see are the bonds between atoms. The sharp points where two lines intersect is a carbon atom. Now you might also ask, where are the hydrogen atoms? Remember that this is a very basic representation of our molecule. When hydrogen is connected to carbon to create a hydrocarbon, it is non-reactive. Therefore, it is not important to the function of sulfur mustard by itself. What is important are the different functional groups within sulfur mustard. A functional group is a group of certain atoms that perform similarly between different molecules. And so we actually have a few functional groups in this molecule. The first one is the sulfide group, which is a functional group consisting of a sulfur atom. There are many sulfide functional groups in the world. This functional group could be more specifically called a thioether, which is a sulfur atom flanked by 2 carbon atoms. We also have 2 alkane functional groups, one on either side of the sulfur. Alkane groups are chains of hydrocarbons where each bond is a single bond. We will talk more about the role of these functional groups in the next section, but know that they are key to sulfur mustard's role as a chemical weapon. Reactive regions are located at the halides. These are areas where the molecule, surprise surprise, reacts. Halides are a group consisting of a halogen combined with another atomic group. Polar bonds are located near the ends of the molecule with a negative chlorine atom and a positively charged carbon atom. The skeletal structure is useful because it is the most simplistic method to represent this molecule. This is a double-edged sword, however, as the simplicity can greatly assist those who know how to read it, but also confuse those who cannot. It is a useful tool in learning the most important atoms within a molecule and how those atoms govern the function. The skeletal structure also shows the bond lengths and bond angles of our molecule. By doing so, it begins to show the geometry of it. However, it does not show the full 3D model. That is the job of our third and final model. This one obviously shows the molecule in a 3-dimensional space, unlike the other 2 models which showed only in a 2-dimensional space. It once again portrays the bond lengths and angles from the skeletal structure, but this time for all the atoms. This and the Lewis dot structure are the only ones to show all the atoms and therefore give a better understanding of the structure as a whole. It is also the only one that shows the relative atomic radii. By doing this, it gives the best representation of the geometry, shape, and size of sulfur mustard. Once again, the functional groups and reactive regions from the skeletal structure can be seen. In fact, you can argue that you can see them in better detail here because the full hydrocarbons are present. Now, size may seem insignificant, but it is actually a very important concept. The size of a molecule dictates where it can fit within the plethora of other molecules making up the human body, where sulfur mustard functions as a toxin. Also, when it attaches itself to other molecules, as we will see later on, it can change their geometry as well. Furthermore, the addition of new atoms to a molecule can fundamentally change its properties. We will see more of this later as well. By itself, the 3D model fails to fully show the structure-function relationship. Similar to the skeletal structure, it does show the most important regions in atoms which dictate certain properties and functions. However, it also lacks the electron behavior that the Lewis dot diagram shows, which is extremely important on learning how sulfur mustard works as a chemical weapon. Now we know both the functions and the structure of sulfur mustard. I've hinted at the various components of sulfur mustard and mentioned that they affect the molecule in some way. Now it's time to learn the specifics of how the structure of sulfur mustard directly results in the infamous chemical agent. For this section, I will first focus on the unique smell of mustard gas. Then, we will combine everything we know about this molecule to learn about how it causes blisters, chemical burns, and other dangerous effects. Let's learn a little bit about smell. As mentioned all the way back at the start, sulfur mustard was reported to smell like garlic or mustard. If we look at our molecule, you should remember that we have a thioether over here. Well, it has been recorded that thioethers and sulfide groups in general produce a very foul odor. Some have described it as bad breath or rotten eggs. Others have found it more similar to the smell of garlic or mustard. Because of this, it is logical to conclude that the thioether is the main reason for sulfur mustard and mustard gases' unique smell. Now let's move on to the more complex function of sulfur mustard, which is all the blistering and burns it can produce. First, let's define the word burn. For most of us, we might think of it specifically as an injury from heat. However, our trusty Merriam-Webster dictionary expands this by saying an injury or damage resulting from exposure to fire, heat, caustics, electricity, or certain radiations. A very important property of sulfur mustard is that it is a nucleophilic alkylating agent. This is when we get into the world of big words and complex ideas. Lots of fun stuff. So a nucleophilic alkylating agent is a substance that transfers alkyl groups to a nucleophilic molecule. Remember that those nucleophilic molecules donate electrons to create covalent bonds. So now, what's an alkyl group? They are very similar to the alkanes mentioned before. However, alkanes refer to just a chain of hydrocarbons. Alkyls consist of the hydrocarbons as well as the rest of the atoms those hydrocarbons are attached to. Sulfur mustard is an alkylating antineoplastic agent. These substances are used in cancer treatment by adding alkyl groups to DNA molecules, resulting in the cell being damaged or destroyed. Now we should introduce the two main molecules sulfur mustard bonds with in order to act as a deadly chemical weapon: DNA and RNA. DNA is called deoxyribonucleic acid. It can be thought of as the memory bank of your genetic material. Everything that governs your physical properties and some mental traits is located within DNA. DNA's genetic material is also important for cells to be able to function and divide. It also contains information to synthesize proteins, which build important organs and facilitate bodily functions. RNA, or ribonucleic acid, is another molecule that is extremely important. Its main function is to carry the instructions for protein synthesis from the DNA housed within a cell's nucleus to the cell's ribosomes. These ribosomes are what actually create the proteins. Note that for both of these molecules, they are nucleophilic, exactly what sulfur mustard likes to bond with. Also, both of them are composed of four nitrogen bases. They share adenine, cytosine, and guanine. They differ in that DNA's fourth base is thymine, while RNA's fourth base is uracil. As an alkylating antineoplastic agent, sulfur mustard loves to bond with specifically guanine. Therefore, the bonding of sulfur mustard with these two molecules is almost the same. We will now see a reaction in chemistry called an SN2 reaction. This is a reaction where a bond is broken and another bond is made simultaneously. If we look back to our Lewis dot structure, we can see that every atom has a full valence shell. However, it is also important to know that atoms prefer to be in the most stable state possible. Because of this, a chlorine anion from either end of the molecule will break away. taking two of the previously bonded carbon's valence electrons. An anion is a negatively charged ion. So now we have a chlorine atom that has a full 8 electrons in its valence shell. It's pretty stable. However, our carbon atom also wants to fulfill its valence shell by gaining 2 more electrons. Our Lewis dot structure shows that sulfur has 2 pairs of valence electrons that are not bonded to anything. Therefore, our impoverished carbon atom flips backwards and bonds with the sulfur, creating a sulfonium ion. This is a positively charged molecule where a sulfur atom is attached to 3 organic compounds. Organic compounds are molecules consisting of carbon, which we have plenty of in this ion. The overall significance of this new ion is that it is reactive, opening the way for it to bond with guanine. Speaking about guanine, here it is. So here comes our sulfonium ion. When bonding with guanine, it heads towards this NH2 group. So basically, nitrogen attached to 2 hydrogens. The carbon atom that moved to bond with the sulfur atom unbonds with the sulfur and bonds with the nitrogen. Nitrogen normally creates only 3 bonds, which it is already doing. However, it is now creating a 4th bond and thus becomes positively charged. It drops 1 hydrogen atom to regain the electrons it was sharing with it and become neutral again. Now our sulfonium ion is bonded with guanine. Therefore, it is also attached to a DNA or RNA molecule, wherever this guanine comes from. The functions of those molecules are inhibited by the addition of these new atoms. Cells have difficulty dividing, genetic material is altered, and protein synthesis is hindered. Some key bodily processes cannot occur. This can damage a cell or even lead to its death. Furthermore, these issues can lead to skin irritation, especially if the cell damage results in a skin tear. Remember those alkane groups from the skeletal structure? Those functional groups are insoluble in water, yet soluble in organic substances. It is likely that they lead to sulfur mustard having this same trait. It can penetrate organic substances such as skin easily. Because of this, it can damage and destroy multiple areas on the skin at once. As the first layer of skin tears, the body sends in fluids as a buffer to prevent damage to lower layers of skin. This creates a bubble of fluid underneath the skin, otherwise known as a blister. Chemical burns are also a result of cell death and tissue damage. These burns can lead to disfigurement, seen in many photos of World War I mustard gas victims. So, in conclusion, sulfur mustard's structure-function relationship is pretty complicated, but it should be expected that to do damage to something as complicated as the human body, there needs to be something just as complex. Thank you very much for watching, and I hope the information I presented was understandable and clear. And have a nice day.